No, Friday's lecture is not, but we'll finish off that material, and you shouldn't have needed Friday's lecture for the homework that was due this weekend, right? So for what we're going to do right now, we'll finish up piggybacking off of what we learned Friday. But it did get recorded, I just haven't gotten around to uploading it. All right. Okay, so we talked about how ethers are not all that terribly interesting as far as functional groups go in terms of the reactions. We are going to learn about two reactions of ethers, one of which is how to create an ether here. So everybody take a second and see if you can't remember which alcohol and alkyl halide you would use to create the following ether. This is what was called that Williamson ether synthesis. All right, so we're going to chop this thing at this oxygen, right? And so these are our two fragments here. But we could have two possibilities. One is that this half, which I'll color in blue here, is my alcohol, and the other half is my alkyl halide. Okay? Or it can be the other way around. This can be my alkyl halide, and that one carbon chunk is my alcohol. All right, so in theory, we got these two possibilities. Which one is it going to be? Remember, we're gonna look at these carbons. This right here has two carbon neighbors. This one actually doesn't have any methyl group, okay? And the higher the degree of substitution, that one's going to be our alcohol. All right, so we said the smaller fragment was our alkyl halide, really the less substituted fragment. Less substituted carbon is the alkyl halide. So in theory, both of these would lead to this same product, but we want the smaller one to be our alkyl halide. So this would be our correct combination of reagents here. I guess I can move it up. Boom. Boom. All right, so now we're going to learn about how to break apart an ether. So starting with an ether, if we treat it with a strong acid like hydrobromic acid, basically have the opposite reaction. This will decompose into an alcohol and an alkyl halide. All right, half of this molecule becomes the alcohol, the other half becomes the alkyl halide. All right, so we're splitting our ether, chopping it into its two parts here. All right, so let's just draw another one. All right, take a second and see if you can't tell me what the product of this reaction would be. All right. So again, we're kind of chopping it at that oxygen. So 1/2 is going to be our alcohol, and the other half is going to be, in this case, that alkyl chloride. It's going to be a chlorine. All right, but importantly, counting carbons, I got 1, 2, 3, 4, 5, 6, right? So all my carbons are accounted for. Okay. So if we take an ether plus an acid, we get an alcohol and an alkyl halide. All right, we're breaking that ether in half. All right, so that's all sort of pretty straightforward. If we have a symmetric ether like we had in these two examples here, there's really only like one possibility for your alcohol and your alkyl halide. They got the same number of carbons. But what if we have something like this? All right, this very asymmetric ether here. How is that going to react with our acid? Okay, because again, we have two possibilities, right? If we think about this again, we're going to chop at the oxygen. I'll just color these on one side and the other side, right? So again, we kind of have the opposite of the question we were asking ourselves before, or it's really the same question, but now looking at the opposite reaction. Which half is going to be my alcohol and which half is going to be my alkyl halide? Because I got two different possibilities, right? Either the blue carbons are the alcohol, are the alkyl halide, and the green are the alcohol, or it could be the reverse. Right, so these are our two possibilities here. Again, if I just take that ether and I split it at the oxygen, either the green carbons belong to the alcohol or they belong to the other fragment, the alkyl halide, right? And so which one's which here? What's my actual set of products going to be? Okay, again, we're going to have to look at the degree of substitution of each one of these carbons. I guess just going over here. All right, so what we're going to do is we're going to build ourselves a little bit of a cheat sheet here. Ether decomposition. Okay. So we have methyl groups, primary, secondary, tertiary, and just like before, we're going to lump in these benzylic carbons in with our tertiary category here. And we're going to create two categories here, the mechanism that this reaction occurs, as well as the reactivity of each of these types of carbons. Okay. So these are, if we look at our example here, let's go back to our simple example actually. Okay, we don't spend a lot of time talking about mechanisms, but if we were to see how this reaction actually occurs in terms of like how the electrons are moving, oops, this bromide ion plays the role of a nucleophile. It attacks this carbon. So if the bromide's the nucleophile, what's that carbon going to be? Not nucleophile, but what's the other one? The electrophile. Okay? And that breaks that bond there. So these are substitution reactions. Okay? And if we go back to our cheat sheet that we made before, which type of substitution, from a mechanism standpoint, which type of substitution reactions do our tertiary and benzylic like to undergo? Those are the ones that are the SN1, right? Everything else, those smaller ones, were SN2. And so we're going to see the same thing here. If we have a tertiary or benzylic, it will be an SN1. Otherwise, it's that SN2 type of substitution. Okay? But again, now we have this sort of like idea of where if we take an asymmetric ether, which one of these carbons is going to be more reactive? This tertiary one over here, or this one? This one's a methyl, right? And so just to be clear, a methyl means that there are no carbon neighbors for that particular carbon, right? This one has these 1, 2, 3 carbon neighbors. That's why it's tertiary. This one doesn't have any, so it's a methyl. Okay? So what's more reactive, a tertiary carbon or a methyl? Yeah, so it turns out that the tertiary are the most reactive of all the possibilities here. So if we have a tertiary, that's definitely what's going to be the one that reacts. That's our most reactive of all of our carbons. okay? But then I think like naturally then you would say, oh, well then a secondary is the most reactive, and actually that's not true, okay? So if we look here, we sort of see a similar problem to what we've seen before with regard to our SN2 reactions, right? This would be SN2 since this is methyl. And remember, a big factor in these SN2 reactions are how accessible that electrophile is it this really crowded carbon that nucleophile is going to have a hard time getting to, or is it nice and exposed and out in the open, right? So depending on how crowded it is, that's going to dictate our reactivity. So it turns out that these methyl ones, they're the most accessible of all the carbons. So they're going to be the next most reactive, followed by primary, and so a secondary carbon is actually the least reactive. All right, it's all crowded and hard to get to. All right. So again, what we're going to see is that our chloride reacts with the most reactive carbon, which is in this case that tertiary carbon. So if the chloride reacts with our tertiary carbon, these will be our products here. Okay, so let's just sort of from scratch here how we would go about approaching these problems. Let me put a new one down. Let's say plus HBr. All right, so the first thing we got to do is we got to split at that oxygen and determine the substitution of the carbons on either side. So step one, I'm going to split it at that oxygen, chop. I'm going to look on either side and determine my degree of substitution here. So this carbon has 2 neighbors, so it's a secondary. All right, I want you all to do this one over here. Take a minute and use a different color. What's that purple carbon? Primary, right? It's just got this 1 carbon neighbor over here. All right, so we split it at the oxygen and determined the degree of substitution on the carbon on either side. And now our more reactive carbon will react with our halide, which is in this case the bromide ion. Right, so according to our table here, which one of these 2 carbons is going to react with our bromide, the red or the purple? The purple, right? If I'm going to compare a primary versus a secondary, the primary is the more reactive. All right, so that's what's going to end up reacting with my halide. So in terms of my products, I'll get my alcohol. I guess I got 2 carbons there, whoops. And my halide, my alkyl halide. All right, and to be clear, these 3 carbons, that's my alcohol. These 2 are my halide carbons. All right, so again, the whole idea of these of ranking these different carbons in terms of their reactivity is that the more reactive one is going to react with our halogen, right? So that primary carbon is what reacts with that bromide. All right, so let's just do a few examples.
Are we going to add more rules other than those 2?
That's it. That's just the process. Yep. Not a. In terms of like predicting products, nothing more crazy than that. All right, we are going to build with what we know about SN2 and SN1, so let's just do an example of that. Not really. Sorry, we'll just do HBr for all these. Yeah, okay. All right, so make sure that you can do the top 2. The bottom 2 obviously have these dashes and wedges, and so there's going to be some stereochemistry consideration we have to make for those, but we'll get to that here in a second. But make sure that you can do these top 2, because those we should be able to do based on what we've discussed. Okay. So for this first one, again, we got to chop at the oxygen and then look on either side and determine our degree of substitution. So let me use different colors. All right, so what's that purple carbon on the right? That's zero carbon neighbors, so we call that a methyl. And what about the carbon on the left, the red one? This is just a primary, so you're only counting carbons. So I get it, it's also connected to that oxygen, but we're only counting how many carbon neighbors it has, right? So in this case, it only has this one carbon neighbor, so this one is a primary. All right, and then what is more reactive, a methyl or a primary? According to our little chart, it's going to be a methyl. All right, so that means that is what that bromide's going to react with. I'm going to stick the bromide on the more reactive end, the methyl group. All right, so then the other part, these three carbons are my alcohol. All right, so again, the trick here for these is that more reactive, that means it's going to become the alkyl halide. All right, the fragment that has that, in this case, bromide on it. Okay, so again, let's chop. Look on either side. This carbon right here that I'm coloring in red on the left. Primary, secondary, tertiary. Tertiary. And then we'll jump to the other side. This thing here, I'm going to color in purple. Primary, secondary, tertiary. Primary. Okay. So then which one is more reactive, tertiary or primary? Tertiary, yeah, that's what I meant. Okay, so that means that this one's more reactive. So given that, everybody just make sure that we can draw our products now that we understand how to connect which side's more reactive to what our product's gonna be here. So just take a minute if you haven't already. All right, so again, that more reactive half, that's what becomes my halide, my alkyl halide. All right, that gets that bromide on there. So then the other one, how many carbons we got? 1, 2. Try to draw it in a similar orientation. Boom. Okay, so now let's do this one together here. Oh, this is kind of going to be a pain, actually. Let me move this thing down. Okay, so first we got to start this off just like before. Gonna chop at our oxygen. Take a second to tell me what that carbon is and what this carbon is. The one on the left, the red carbon. So benzylic would have to have the benzene ring in there, right? It is really weird because we got dashes and wedges, but let's just count neighbors, okay? Whoops, that's not gonna work. All right, so looking at this carbon here, this would be 1, this would be 2, and this would be 3 carbon neighbors. So this would be a tertiary carbon here. And what's the purple? So this would be a methyl. All right. So now when we draw our products, I'm going to draw them below just so that I have more room. Remember, tertiary undergoes what type of mechanism? SN1, and this is kind of asked backwards here, but when we do SN1, how many products are we drawing? 2, right? So we got to draw both stereochemistries for our SN1. Okay, so the 1 means 2 products. I didn't make the rules. Okay, so because that tertiary half is more reactive, it's going to have that halogen on there. But again, I'm going to draw both possibilities. And then there's just the 1 for my alcohol.
The example above that one, why didn't we do a SN1?
There were no dashes and wedges, so there was nothing to kind of flip around. So not all molecules have these dashes and wedges associated with them. So for the 2-semester course, you kind of would have learned this sort of ability to spot whether or not they have them. For us, you're just kind of going to trust me when I draw them that molecule, you got to worry about it. If I didn't draw them, you don't have any stereochemistry to consider. Right, so since I specifically gave you dashes and wedges here, that's why you got to worry about it down below. Okay, so now we get these mixture of these 2 for our alkyl halide. We only have that 1 for our alcohol. Okay. This is going to be a pretty rare situation up here. Specifically, if you have that tertiary and you have that stereochemistry, you got to worry about it. I think more common is this right here. And so let's do this example. We're going to go through first, do it exactly like we did before, split it at this oxygen, assign the substitution for this side and this side. All right, what's the red side? Secondary, yep, this one and this one. And this side is our methyl, okay? So then which side is more reactive? The methyl, all right? And so the key here, we want to make a note, is only worry about stereochemistry, right? By that I mean the dashes and wedges for the alkyl halide fragment. Whoa. Okay, so what do I mean by that? So if we look at our chart, we can say that this is an SN2. Okay, and SN2, we know we got to invert our stereochemistry, but we're only going to worry about it for the alkyl halides part. So for our alcohol, we're just going to leave it as it is. So there's not anything really that we have to do here other than to make sure to keep that wedged bond as a wedge. Right? It was the methyl fragment that got reacted with. So that's the one that I would have to worry about stereochemistry with. The alcohol portion just stays the same. All right, so we're only going to worry about stereochemistry if it's on the alkyl halide fragment, like it was above, right? We had to draw both our products because that's where our alkyl halide was. If it's on the alcohol part, you just leave it the way it was.
So it stays the same in the way.
So it stays the same because it's the alcohol half.
Not necessarily it's reductions for the substitution this way.
Oh, yeah, so for the substitution, you're only going to worry about it if it's the alkyl halide fragment. In this case, it wasn't. It was the alcohol part, so you just leave it as it is. All right? Only with the alkyl halide part do we have to worry about it. All right, so then let's just do one more.
What's HBI?
Oh, yeah, sorry. You do need an acid there, but yes, we'll just default to that one. Could be, I mean, I guess for the sake of whatever practice, it could be HCl or HI, but yes, just a halogen. All right, so that red carbon is what? Primary, secondary, tertiary? Secondary. And what about the purple one? Primary. Okay. So then which one is going to react with my chloride, the primary or the secondary? Primary, the more reactive one. Okay. So then what am I going to do to this dashed bond? I'm going to leave it, right? If it's the alcohol portion, you're going to leave it, right? Only worry about it when it's the alkyl halide. So my alcohol here just stays that dash. All right, so we said only worry about stereochemistry for the alkyl halide. Let's actually just say explicitly here Leave alcohol fragment alone. Don't touch it. Don't mess with it. If it's a dash originally, it's going to be a dash in the product. If it's a wedge originally, it's going to be a wedge in the product. Okay, so we'll finish up. We got one more set of reactions for this chapter. We're kind of slow playing this chapter because there's kind of a lot going on. I didn't want to cram too much in one. For right now, though, so you should have, y'all are kind of going to be my guinea pigs here in terms of whether or not I sent this successfully. But if you look at your Canvas announcements, your most recent announcement